So to continue our discussion or the solving of problems involving Newton's laws of motions, we will solve at this time a problem still involving tension and the law of motion, but with an angle. Remember that in the previous examples, we solved about problems dealing with tension involving two blocks connected by a massless, frictionless string. One of the cases was wherein the mass was hanging, one of the masses was hanging, and the other one was resting on a frictionless horizontal table. And the other one was wherein the two blocks were hanging, still connected by a massless, frictionless string passing over a frictionless pulley. This time, our problem is about a car. So a rope whose working strength is 3,300 newtons is used to tow a 1,000 kilogram car up an 18-degree incline. Find the maximum acceleration that can be given to the car. So this working strength of the rope, 3,300 newtons, is the tension of the rope. It's used to tow a 1,000 kilogram car. So very important, in any problem, we have to draw first an FBD. So let's say that, okay, this is the horizontal. Let's make this the horizontal, and this is the incline. And this is 18 degrees. So let's say that this is the car. That's the car right there, and it's being pulled. Okay, using a rope. So let's say that this is the rope. The tension there is 3,300 newtons. And the mass of the car, the mass of the car is 1,000 kilograms. Our question is, find the maximum acceleration that can be given to the car. So we always make a balance, make an equation out of all the forces acting on the car. So remember that this is the car. And remember that the weight is always directed downward. Okay? So if it is being pulled by the rope in this direction, then therefore the acceleration of the car would also be in that direction. And it is the net force that is going to cause that acceleration. But the net force is not equal to the tension. Why? Because there is an opposing force here. Now, even if this incline is frictionless, there is still an opposing force to the tension, to the pulling force of the rope, and that is the weight of the car. But the weight of the car is not directed in this direction downward. It's directed directly downward, vertical, 270 degrees. So to make an FBD of all the forces here, we have this tension, and we have this weight. But we cannot make an equation out of this. So now all the forces must be parallel to each other. So what are we going to do? So let's zoom this. So if we draw, okay, if we draw a vertical line downward, that would be the weight of the car. But this weight of the car has two components. Okay, let me draw this. We are going to draw a line that is parallel to the incline, and perpendicular to the incline. Okay, let's make it like that. These are actually two components of this vector. So if we look at it on the side note, if this is 18 degrees, then this angle here is also 18 degrees. Now, question is why? So remember that this portion here, they're perpendicular to each other. These are the components now of the weight vector of the car. So you see, if this is 18 degrees with the horizontal, then if we make a horizontal line here, this line here, this is also 18 degrees, right? And what is the complement of 18? What's the complement of 18? That's 90 minus 18. That's 72 degrees, right? So meaning this is also 72 degrees. Now this triangle here is also another right triangle. That's also right there. So if this is 18, this is also 72 degrees here, right? And this is a big right triangle. This is the 90-degree angle here. So if this is 90 degrees here, and this is 72 degrees here, meaning this angle is 18. Okay? So, let's erase all of that. Okay. Now let's label this vector. What is this vector? Our focus is this vector because this is the vector that is parallel to the incline, parallel to the rope tension, parallel to the net force. But this vector is directed towards the opposite direction of the tension. This is directed downwards. So let's say that this is FWY. Now, why is it Y? Because if this is a right angle here, and this is an angle 18 degrees here, this is the opposite side, right? And remember that this downward vector, that downward vector there, that is FW, which means that FWY is FW sine of 18 degrees. Why man? Because sine of 18 degrees is equal to, what's the opposite side of 18 degrees? This one, diba? Which is FWY. What is the hypotenuse? It's FW. So FW sine 18 over, FWY over FW. So FWY equals FW sine of 18 degrees. You simply need to transfer FW here. Alright? So we can now make an equation out of our forces. So the net force is here, is directed upward. The car is going in that direction, meaning tension is greater than this FWY. So FWY, F net force is equal to the tension minus FWY. Tension is F net is MA. We have the tension minus, what is FW? This FW sine of 18 degrees. So again, MA equals tension minus, what is FW? That's the weight, that's mass, times acceleration due to gravity. Sine of 18 degrees. We're not looking for the tension, we're looking for acceleration. So acceleration is equal to tension of the rope minus the mass of the car times the acceleration due to gravity, sine of 18 degrees, divided by m. So what is tension? Tension is 3,300 newtons minus the mass is 1,000 kilograms times 9.81 meters per second squared. Sine of 18 degrees divided by the mass, which is again 1,000 kilograms. So compute using your calculator what is the acceleration of the car. So input in your calculator as it is. Make sure that the mode of your calculator is in degrees because the angle is in the unit degrees. So 3,300 minus 1,000 times 9.81 sine of 18 degrees divided by 1,000. Your answer is, let's round it off up to the fourth decimal place. That's 0.2685. And the unit is meters per second squared. Okay, next problem. This time it's not moving. We simply have to solve for the tension. But we have three cables here. A traffic light weighing 100 newtons, this one, hangs from a vertical cable tied to two other cables. So we have a vertical cable tied to two other cables. The upper cables make angles 37 degrees and 53 degrees with the horizontal. Find the tension in each of the three cables. So we will have two FBDs here. One FBD is the point of connection between the traffic light and the rope here, T3, and the other one is in this point of connection of the three cables. So let's consider this. Let's say that this is point A here. Let's make this point A here, the connection between the traffic light and T3. And let's make this connection among the three cables be point B. That's point B. Okay. So let's make an FBD for point A. So at point A, for point A, so what are the two forces? First, it's the weight of the traffic light, and directed upward is T3, which means that T3 is simply equal to the weight of the traffic light. So since the traffic light is weighing 100 newtons, that's already given, so T3 therefore is equal to 100 newtons. So we already have an answer for T3. Okay, next, we look at point B. So for point B, okay, this is the point B. T3 is now directed downwards. That's T3. And then we have T2. Okay, now that's T1. And then we have T2. So if the angle formed by T1 with the horizontal here is 37 degrees, it means that if we draw a horizontal line here, this is also 37. And for T2 here, the angle formed with the horizontal on the side is also 53 degrees. Okay? So that's 37 degrees, and that's 53 degrees. Now, the how are we to find the values for T1? How are we to find the magnitude of T1 and T2? Okay, so because these are oblique, no, lines, so which means that it has a vertical and a horizontal component. Now, for the horizontal component, we're going to make a summation of the horizontal components. So, T2 cosine of 53 degrees, that's positive, no? Directed towards the right. Okay? And then T1 is going to the left, so minus T1 cosine of 37 degrees. Does T3 have a horizontal component? Wala, no? And since this is not moving, it means that there is zero net force. So this equation for the horizontal component, we're able to come up with an equation that relates T2 and T1. This gives us a relationship now for T2 and T1. Okay, next is we're going to make an equation for the vertical components. Vertical component. So, because it's not moving, meaning the summation of all vertical components will be equal to 0. So starting from T1, the vertical component of T1 is directed upward. That's T1 sine of 37 degrees. And plus T2 sine of 53 degrees. And then This is directed downward. We don't need an angle for this anymore because it's vertically, no, directed downward. So that's minus T3 equals 0. So it's up to you which of the two values you want to solve first. Let's say I want to solve for T1 first, so we can express T2 here in terms of T1. So let's say T2 equals T1 cosine of 37 degrees over cosine of 53 degrees. Let's make this equation number 1. So let's say this is equation number 2. So substitute equation number 1 to equation number 2. So this is already what we call class solving systems of linear equations. So we have two equations and we have two unknowns because T3 is already given, which is 100 newtons. So T1 sine of 37 degrees plus T2, substitute, is T1 cosine of 37 degrees over cosine of 53 degrees times sine of 53 degrees minus T3 is 100 newtons equals 0. So we have T1 sine of 37 degrees plus T1 cosine of 37 degrees. What is sine over cosine, class? That's tangent. We can only do that because they have the same angle, 53. So tangent of 53 degrees equals 100 newtons. Actually, you can just input this in your calculator, no, but I'm showing this because you can use this in your other classes. So we factor out T1, we have sine of 37 degrees plus cosine of 37 degrees tangent of 53 degrees equals 100 newtons. So T1 therefore is equal to 100 newtons divided by sine 37 degrees plus cosine of 37 degrees tangent of 53 degrees. So input in your calculator. Again, make sure that your calculator is in the degree mode because the unit of our angles is in degrees. So 100 over sine 37 plus cosine of 37 tangent of 53 degrees. So our first tension is 60.18 newtons. That's T1. So solving for T2, okay, solve T2 using equation number 1. So T2 is equal to 60.18 newtons times cosine of 37 degrees divided by cosine of 53 degrees. That's equal to, okay, again, solve using your calculator. And make sure that you're using the exact value, not the rounded off value. So you'll be able to get 79.86 Newton. And you can always check your answer, class, if your answer is correct or not by substituting in our equation. So you can try to check by substituting in this equation and check if it's really equal to 0. Can you try to check if it's equal to 0? So you multiply your answer T2 cosine 53 degrees and your answer T1 cosine 37 degrees. Is it equal to 0? Or T1 sine 37 plus T2 sine 53 minus T3, is it equal to 0? So if both equations are satisfied, it means that our T1 and our T2 are correct. So, and then we also have T3, which is 100 newtons.